bertugas sebagai moderator yang akan memandu jalannya acara kita pada siang hari ini. Oke, jadi forum kali ini mengangkat tema yang sangat menarik bagi kita semua, yaitu millimeter wave on silicon high frequency application in semiconductor technology yang akan disampaikan oleh narasumber kita yang istimewa ya dari luar negeri. Nah, acara ini merupakan bagian dari upaya FORTEI dalam mendorong perkembangan ilmu pengetahuan dan teknologi terkait kolaborasi antara sivitas akademika serta praktisi di bidang teknik elektro khususnya. Nah, untuk mempersingkat waktu, mari kita melangkah ke acara selanjutnya yaitu sambutan. Nah, sebelum kita masuk ke sesi utama, mari kita mendengarkan sambutan dari Ketua Umum FORTEI, Bapak Profesor Dr. Engineering Insinyur Arif Udianto STMT IPU. Oke, waktu dan tempatnya saya persilakan, Prof.
Baik, terima kasih banyak Saudara MC Pak Muhira. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, selamat pagi waktu Jerman, Prof. Selamat sejahtera
Pagi ya.
semuanya. Selamat bertemu kembali Bapak Ibu sekalian di acara FORTEI Monthly Forum. Ini adalah acara bulanan kita ya, tempat kita untuk saling sharing, mengupdate tentang perkembangan teknologi terbaru. Nah, kita menghadirkan berbagai macam topik ya, dan juga berbagai macam latar belakang pembicara. Seperti kita tahu bahwa di teknik elektro ini ada banyak sekali bidang, dan kita sudah mulai dengan bidang energi pada saat itu. Alhamdulillah pada siang hari ini kita akan membahas satu topik yang juga sangat menarik yang berkaitan dengan semiconductor. Millimeter wave on silicon high frequency application in semiconductor technology. Sekedar informasi Bapak Ibu sekalian bahwa saat ini di Indonesia juga sudah ada konsorsium semiconductor, kalian lapor Prof. Herman ya. Kebetulan saat ini Prof. Trio ini sedang di IMEC nih, sedang di Belgia, sedang menjajaki kerjasama dengan IMEC. Sudah ada sekitar 16 perguruan tinggi yang tergabung dalam konsorsium tersebut. Di topik hari ini akan memperkaya ya kita semuanya terkait dengan perkembangan teknologi khususnya di bidang semiconductor. Sebagai informasi Prof. Herman, bahwa FORTEI ini merupakan forum pendidikan tinggi teknik elektro Indonesia. Jadi anggotanya memang adalah para kapoldi, kemudian dosen, dan para pegiat ya, di bidang elektro, itu seluruh Indonesia yang hadir hari ini dari berbagai macam perguruan tinggi. Ya, mudah-mudahan nanti apa yang Prof. Herman sampaikan itu bisa memberikan update kepada kita semua ya terkait dengan perkembangan teknologi semiconductor, khususnya barangkali yang terkait dengan millimeter wave, terutama di bidang silikon ya. Nah, silikon ini merupakan salah satu material utama di semiconductor kita, dan kelihatannya masih akan bertahan beberapa waktu yang akan datang meskipun diteliti bahan-bahan yang lain yang diprediksikan juga akan bisa mengganti peran daripada silikon, tapi kelihatannya masih perlu waktu. Baik, selamat mengikuti acara FORTEI Monthly Forum hari ini. Semoga kita semua mendapat pencerahan dari Prof. Herman. Sekali lagi terima kasih banyak Prof. Herman untuk kesediaannya menjadi narasumber kita hari ini, dan kepada semua panitia, Prof. Lianta, Pak Muhira ya, dan teman-teman dari Direktorat. Terima kasih, saya cukupkan. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang.
Ya, Waalaikumsalam
Waalaikumsalam.
warahmatullahi wabarakatuh. Iya, terima kasih banyak, Prof. Oke, jadi apa selanjutnya kita masuk ke acara inti. Ya, di sini kita telah hadir narasumber kita, Profesor Dr. Herman Jalli Ng, di mana beliau merupakan salah satu ya akademisi dari Karlsruhe University of Applied Science. Nah, untuk pemaparan beliau, ya insya Allah akan didampingi langsung oleh Profesor Yulianto Siregar. Nah, untuk mempersingkat waktu dan tempatnya, saya persilakan Prof. Yuli untuk membawakan acara. Terima kasih.
Oke, baik. Terima kasih Pak Mahira. Terima kasih Prof. Arif atas sambutan dan memberikan waktu ke kita untuk menyelenggarakan kegiatan pada hari ini. Ya, pada tadi sudah disampaikan sama Prof. Arif, ini kegiatan bulanan. Baik, sekedar informasi saya ingin memperkenalkan sedikit apa namanya ke materi kita. Mungkin kelihatan ya, Pak
Ya,
Muhira, kelihatan ya. Oke, ya,
kelihatan.
oke siap.
Kelihatan.
Kelihatan sama
Ya,
Prof.
ini kurikulum vitae dari Pak Profesor Herman Jalli. Pak Herman Jalli lahir di Tebing Tinggi, ya tahun 1981. Lalu dia Prof Herman, dia sekarang sebagai profesor di Oslo. Oslo. Saya agak susah menyebutkan ini Prof Herman karena sedikit bahasa Jerman ya. University of Applied Science Jerman. Eh, Prof Herman ngambil, saya rasa Prof Herman silakan untuk mempresentasikan apa namanya gagasan atau ide-ide mengenai bukan itu apa bidang-bidang mengenai semikonduktor. Silakan Prof Herman.
Ya, oke, terima kasih.
Ya, silakan Prof.
Iya. Kelihatan ya?
Ya, kelihatan Prof.
Ya, terima kasih Pak Profesor Yulianta Siregar. Terima kasih Pak Profesor Arif Budiarto dan Pak Muhira serta rekan para profesor, dosen-dosen, saintis, mahasiswa. Selamat siang. Saya ucapkan
Ya,
nama saya Herman Jalli Ng, lahir dan besar di Kota Tebing Tinggi, Sumatera Utara. Um, Mohon maaf terlebih dahulu, saya sebenarnya masih fasih bahasa Indonesia, tapi um, vokabulari bahasa Indonesia saya sangat terbatas. Jadi nanti waktu isi presentasinya saya mau memberikan dalam bahasa Inggris. Jadi mohon understanding ya. Jadi karena sangat susah bagi saya untuk tukar menukar bahasa, jadi saya stay aja dalam bahasa Inggris gitu ya. Tapi
siap, siap Prof.
saya akan mencoba sebanyak mungkin menggunakan bahasa Indonesia. Nanti Bapak Ibu jika ada pertanyaan boleh silakan pakai bahasa Indonesia. Kalau nanti saya tidak mengerti, saya akan minta Profesor
Siap,
Pak Yulianta
ya,
mentranslate buat saya.
ya, siap Prof.
Oke, jadi begini saya sejak tahun 2020 ini saya telah bekerja di Hochschule Karlsruhe, University of Applied Sciences. Itu di universitas dulu 25 tahun yang lalu saya juga kuliah. Jadi saya kuliah di universitas yang sama. Saya jadi menggantikan profesor saya dulu yang dulu memberikan kuliah di bidang Advanced Electronic Integrated Circuits di Fakultas Elektro yang sama ya um, jadi um, bisa dikatakan balik kampung ya, tapi balik kampungnya masih tetap di Jerman, di universitas yang sama. Um, Sekitar tahun sekitar tahun 2005 saya menyelesaikan kuliah saya di Karlsruhe. Saya pindah saya join perusahaan Bosch di Reutlingen dan bekerja sebagai IC Design Engineer beberapa tahun. Setelahnya saya memutuskan untuk terjun ke riset di bidang millimeter wave transceiver design di teknologi silicon germanium by CMOS. Nanti saya akan ngomong lebih detail tentang ini. Um, ya, saya jadi pindah ke bidang riset dan di tahun 2002, jadi saya pindah ke bidang riset dan bekerja di perusahaan Infineon. Infineon punya Research Institute di Austria, itu sebenarnya perusahaan Jerman, tapi perusahaan Jermannya mengirim saya ke Austria dan saya pun jadi bekerja sama dengan Universitas Johannes Kepler University of Linz, di mana saya menyelesaikan PhD thesis saya di bidang ya millimeter wave transceiver design for radar application. So untuk aplikasi radar di tahun 2014 saya pun selesai, dan setelah selesai saya memutuskan saya mau balik lagi ke Jerman, dan saya pun jadi senior scientist di perusahaan IHP Saya akan ngomong lebih banyak nanti tentang perusahaan IHP ini karena perusahaan ini benar-benar sangat penting bagi saya. Sampai sekarang pun setelah saya memutuskan untuk pindah ke universitas, saya masih mempunyai hubungan yang baik dengan IHP. IHP itu adalah sebuah research institute, tapi juga mempunyai bagian yang komersial yang juga bisa membuat chips, semiconductor chips, dan uh, perusahaan IHP ini, Research Institute ini juga memberikan saya dan murid-murid saya akses ke silicon chip area, ya, dan juga ke akses ke teknologi silicon germanium ini. Jadi kami masih student saya dan saya juga masih bisa membuat chip di perusahaan ini, ya. Uh, jadi saya mau switch ya sekarang ya ke dalam bahasa Inggris. Ya, Anda mungkin dah menyadari saya juga agak ya kesusahan ya bahasa ya.
Ya,
Uh,
siap, Prof.
Oke, good. Ini here on the bottom left, you can see two photos of chips. Yeah, the left one is a smaller chip, bonded, wire bonded, and packaged in a standard QFN package. The right one, the larger one, it has a size of 25 square millimeters, so 5 times 5 millimeter. Size, um, but it has all the functions of a complete radar device. Yeah. Um, in this talk, I will not talk too much about the wave propagation on silicon, but I would rather address the practical aspects of silicon sensor technology. Okay, so this is the content of my talk. After a short introduction, I will talk about the advances that have been achieved in the silicon semiconductor technology in the last few years. Then I will present one particular application in very high frequency range. I will present the millimeter wave sensors. Afterwards, I will give you a few words about my current research and teaching in integrated circuit technology. And then finally, I will end my talk with a summary and outlooks. Okay. So a couple years ago, after the Corona crisis, we also faced another crisis in the semiconductor industries. Yeah, during this crisis, most people found out where all the semiconductor chips can be found in our life, and that our life is so dependent on the chips. These are some screenshots of news in Germany. Here, for example, you see the daily news and the Tagesschau reported about the chip shortage in the car industry, that many cars could not be built because the chips are missing. Yeah, the chips were missing at that time. The chip shortage affects many industries, from computers, cell phones, automotive to household appliances. Yeah, laptops, for example, laptops and PCs were in very short supply. Those with the latest chips were not even available. Yeah, Apple here even had to cut the iPad and iPhone productions because of lack of chips from TSMC. Yeah. The Frankfurter Allgemeine Zeitung is a very well-known German newspaper. Even told the Germans to gently stroke our dishwasher every morning. Jadi orang Jerman itu sangat menyukai dan sangat tergantung dengan mesin pencuci piring dan mesin pencuci baju mereka. Jadi ini koran Jerman, Frankfurter Allgemeine Zeitung, menyuruh mereka untuk ya tiap pagi mengelus ini mesin pencuci pada saat itu, ya itu 2 tahun yang lalu. Jadi supaya ya jangan rusak dulu ya di mesin cuci ini ya, karena 2 tahun yang lalu di Eropa benar-benar krisis, tidak punya chips spare parts untuk mesin-mesin pencuci ini ya. So at that time during this crisis, yeah, people learned then that the European countries and the companies actually depend so much on the semiconductor chips, mostly from Asia, from TSMC, from Samsung, from SMIC, and most of the semiconductor chips are not even fabricated in Europe. Yeah, so they are quite dependent on Asia, and that has to be changed then now. Yeah, so okay, very short about what is about what about the IC, or a different name, a chip. We call it also integrated circuits. It is basically just an electronic circuit that consists of many different electronic components such as transistors, diodes, resistors, capacitors, inductors, that are all fabricated on the same silicon substrate. Yeah, so it can be also different semiconductor substrate, but mostly most of these components can be nowadays integrated on the same semiconductor substrate. This is made possible by the many advances that have been achieved in the silicon technology. Yeah. Practically all technical devices contain one or more integrated circuits. Yeah. For example, television, as you know, has chips for the to drive the LCD display. Most television nowadays has processors for the smart TV functions. There is a chip for the power management of the television. Laptops, for example, has many different chips for the processor, for the memory, for the battery management. Car also has a lot of chips inside, mostly chips for the sensor applications. Yeah, these make the technical devices smaller, yeah, cheaper, faster, and more power. Yeah, the technical device becomes more efficient and robust. Yeah, it is interference proof, so-called. Yeah, and when you put an IC inside your technical device, then it is also quite hard to copy your technical device. Yeah, because you can barely see what is actually inside the microchips. Yeah. There are several possible semiconductor-based materials for the realization of the integrated circuits, but nowadays silicon is the most commonly used substrate. Yeah, silicon is abundantly available and cheap, and it is quite easy to process silicon nowadays, and a lot of experiences have been gathered to process silicon, and nowadays silicon is not only used to fabricate the transistors, most of the electronic components that you can think of, resistor, capacitor, inductors, can be all fabricated on the same silicon substrate. Yeah. Yeah, high frequency application require very fast components. Yeah. Previously, these applications were usually reserved for the special 3-5 compound semiconductors, such as gallium arsenide. Yeah, gallium arsenides, however, doesn't allow high density, high integration density. Gallium arsenide enables a very high charge carrier mobility, but you cannot integrate many different components by using gallium arsenide technology. So the integration level is actually quite low. Yeah, and the production yield rate by using gallium arsenide is also quite low. So it means the production cost with the gallium arsenide is actually quite high. Yeah, so that's why not so many companies can afford this. But nowadays, due to the improvements in the silicon technology, the downscaling of the structures of the silicon technologies, made the transistor very, very fast. Yeah, so it means suddenly this low-cost silicon technology becomes very interesting also for analog application, high-frequency applications. Yeah, so it means the silicon technology that is mainly actually used to implement digital IC like processors, memory, and so on. This technology, this low-cost silicon technology can nowadays also be used for the high-frequency applications. Yeah, it has been demonstrated before, and we also already have a lot of commercial application in millimeter wave frequency range that have been implemented by using silicon technology. And this was actually a great deal for many companies here in Europe. For example, a German company, Infineon. This company used to own many semiconductor plants for gallium arsenide, indium phosphide, and so on. Infineon suddenly just decided to abandon all these 3-5 compound semiconductor technologies. They sold all the technology, the semiconductor plants, and then only focus on silicon technology. Yeah, it is not like a poor silicon technology. I will tell you about it later. But since silicon is used as a substrate, it somehow enables many different integration on the same chip. You can suddenly put the complete transceiver on the silicon chip, and also the transceiver and also the digital signal processing processor and everything on the same chip. Yeah, so this is just one example how actually a typical high frequency technical device actually are usually implemented. It's quite an old one, and then you see that most of the chips are put on several packages. These are not integrated into one single chip, but nowadays the latest smartphone actually has many different chips integrated into, let's say, a minimum amount of chips. Yeah, it's not only in this spatial, let's say, application, but also radar application, satellite communication can nowadays also use the same silicon chips, silicon technologies, and then this silicon technology has to be somehow certified for space application. But this has also been done in the couple years ago. Yeah, so I will tell you more about this. Yeah, the interest in the millimeter wave frequency band has risen sharply in recent years. As you know, the spectrum allocation is strictly regulated. So you can't just simply transmit at any frequencies and make your application as you wish. Yeah, so you need to somehow get the license for that. This is one example of the spectrum allocation in Europe. The lower frequency range here, at 0 Hz up to somehow 300 kilohertz, these are quite already full, and also between 300 kilohertz till, let's say, till 3 gigahertz spectrum, these are also already quite occupied with many different applications. We have spectra reserved for broadcasting, AM, FM, radio, television. We have spectrum reserved for mobile communication, for weather, for positioning, for military, for space application, for many different stuff. So at lower frequency range, uh, yeah, mostly the spectrum is already quite full and occupied with applications. At higher frequency range, let's say at frequency range above 30 gigahertz, this frequency range is also called millimeter wave frequency band. Yeah, from 30 gigahertz until 300 gigahertz. If you convert this frequency into wavelength information, 30 gigahertz corresponds to 10 millimeter wavelength, and 300 gigahertz corresponds to 1 millimeter millimeter wavelength. And this spatial frequency band is called millimeter wave frequency band, and now the interest in this frequency band somehow becomes quite high because the silicon technology somehow allows the range. Yeah, there are already some spectra that are already occupied by some application. For example, the 77 gigahertz until 79 gigahertz frequency band is reserved for radar application, for automotive radar application in Europe and in US. We have 60 gigahertz uh, also reserved for some application, home entertaining, for example, but it is unlicensed. We have 30 gigahertz frequency band reserved for 5G, and there are many active research going on using CMOS technology in these frequency bands. Since the frequency bands has quite a huge bandwidth, there are still many possibilities in this frequency range. Yeah. For example, in the mobile communication, to cope with growth rate in the mobile data traffic, the mobile network somehow has to be expanded into millimeter wave frequency bands, and this is certainly the strategy of the 5G communications system. If you move it into millimeter wave frequency band, you have enough bandwidth, and high bandwidth means high data rate. So that is actually the main reason that we will find in the future that that our 5G mobile communication and 6G, this is ongoing right now, the research, this will be poorly implemented in the millimeter wave frequency band. In sensor application, we have automotive radar sensors that have been successfully implemented. It has been also available. It is actually available already commercially. Radar sensor has been successfully used in adaptive cruise control, for example, in collision warning system, in emergency brake assist systems in cars. For autonomous drivings, there are still a lot of potentials for the radar sensors due to the high bandwidth that is available in this frequency range. Yeah, so with the high bandwidth that you get for the sensor application, you get a huge amount of resolution. So you can actually achieve a very high resolutions. You can when you also implement your application in a millimeter wave frequency range, you know that the wavelength becomes smaller and smaller, and then suddenly you can also miniaturize your chips. Yeah, at certain frequency, the wavelength becomes so small that, for example, you can even integrate most of the passive components, the sensor components like the antenna, directly on chips, and then suddenly you have a very small device that you can even hide everywhere. So you can nowadays make, for example, a portable baggage scanner at airports that you can carry all the time. It is so small. You might have seen this radar scanner in the airport, and this is a non-invasive sensor. Unlike X-ray, it is not really dangerous for your health. Yeah, and there are, I will tell you more later about many different applications that we can address by using millimeter wave sensor. Let us go first to the silicon semiconductor technology. Why is it then the silicon technology becomes very interesting for millimeter wave applications? Yeah, so this is the list of silicon semiconductor plants and the technology nodes. So in the 1970s, 1980s, the technology nodes were in the range of micrometer. So 3 micrometer, 4.5 micrometer. With the technology node, I mean here the smaller structure that can be fabricated with a very high production yield rate. So the technology node usually means the smallest channel length of a field effect transistor that can be fabricated. Yeah. So in the 1970s, 1980s, this channel length were in the range of micrometers. That's why the technology was called also microelectronics. This technology nowadays has been the technology node has been shrink many times nowadays. State of the art, 5 nanometer technology node, which actually means the transistor becomes so small, but the name of the technology uh, is still called microelectronics. Actually has to call the technology now nanoelectronics. These are the list of the current technology nodes that are being used here in the world. So 180 nanometer technology node is you can still find it actually a lot in Europe or in Asia. There are many players, many semiconductor plants. You might also know the names here. Some Japanese companies are quite visible here. We have also Infineon, a German company, XFAB, another German company, IBM, but IBM already given up the semiconductor industry, and the TSMC, of course, the largest one. Yeah. And then with smaller technology node, you see that there are less players, there are less companies. For example, at 5 nanometer, there are nowadays only these are not really the latest list. There are actually only 3 companies that can fabricate chips at 5 nanometers. TSMC, the largest semiconductor company in Taiwan, so Taiwan Semiconductor Manufacturing Company, together with Samsung. Samsung is always playing catching up. And then we also have Intel, but Intel has some issue with the production. The yield rate is quite low right now. You see, with the 5 nanometer technology node, the applications fields also not really that high. That's why not many companies invest in this technology node. Yeah. Due to sanction, as you know, the Chinese company, the SSIMC, this is also another quite large company, cannot fabricate chips at very low, very small technology, like 5 nanometers. The yield rate is high at 14 nanometer, 10 nanometer, but not lower. Here in Europe, the latest or the most significant company that can fabricate with the latest technology node is the ST Microelectronics. This one, STM. This French Italian company. It has many fab also in Switzerland, in Germany, and in France, and in Italy. Infineon mainly fabricate chips at 130 nanometer. I will tell you more about this later. Okay, let us move to the basics. You know that silicon is ideally suited for electronic components, mostly actually interesting for field effect transistors. There's a couple of reasons why silicon becomes so dominant. Yeah, the very first semiconductor material that was actually used for transistor was not silicon, but it was germanium. But silicon is more interesting because it is easier to process, and you can easily fabricate kind of oxide layer or isolation layer on top of the silicon. This is the base of how field effect transistor is fabricated. Yeah. This is the starting material, yeah, what we call silicon wafer. It is a silicon disc with a diameter of 8 to 12 inch. It has a thickness of typically 1 millimeters. this wafer can be bought by the semiconductor plant. Usually this is not fabricated by the semiconductor plant itself. They just simply buy it. And this pure silicon is actually not really interesting for electronic components, because the density of free moving charge carrier is actually really quite low. That's why you need to somehow dope this or impurify this with some foreign atoms to make it actually very interesting for electronic components. So typically the silicon is actually doped weakly with boron atoms, for example, and then this is our base substrate. Yeah, so our base substrate is not an intrinsic silicon, but it is a p-dope silicon. And in this p-dope silicons, you implement two n-dope semiconductors areas by using ion implantation. These are how the source and drains of a NMOS transistor are implemented. And then on top of that, you build here the silicon oxide, which is actually just an isolation layer. And then on top of that, you place the gate electrode. This is the NMOS transistors. Yeah. For the PMOS transistor, the drain and the source are p-dope semiconductors, so you cannot really simply fabricate these two n-dope semiconductors directly in the substrate. But before that, you implement an n-dope reagents. This is what we call an n-well, and this is how then the two complementary field effect transistors are implemented in the silicon technologies. Yeah. Nowadays you cannot you can only nowadays you can not only implement the transistor inside the chips inside the silicon technology, you can also implement all passive components, everything that you might need for your electronic components, resistors, capacitors, whatever you can think of. These can all be integrated in the same silicon substrate. So over the years, the process technology has been improved many times to such an extent that now people understand which dosage of dopants, which gases, in which quantity and at which temperature deliver the best results. Yeah, the fluctuation in the process parameters becomes smaller, and people dare to shrink the transistor more and more. Yeah. The lithography also supports this miniaturization with better optics and with better laser technology. Okay, so when you shrink the transistor, so this is how the transistor look like in 3 dimension. Yeah? So you have here the length, the channel length between the source and the drain, and the transistor of course also has a width. The channel has a width. When you shrink the length and the width, then the complete size of the transistor also becomes smaller. When you think of a certain chip area, when the transistor becomes smaller, then suddenly you can also integrate more transistor on the same silicon chip area. Yeah, either you make your chip smaller. This is something that probably you won't actually do, because the chip size actually not really dominated by the transistor itself. The chip size is usually dominated by the interface that you might need, the pads, for example, for the connection to the outside electronics. So it means when you have the space, then you can actually also implement more functionality. So you can integrate even more features inside your chips. You can everything that you can think of, memory, signal processing. You can even put all the analog components that you might need. Yeah, for example, for the implementation of the digital circuits, you need for example, the power supply. This power supply can be implemented by using linear regulator. This is something that can also be integrated in the same chip. You get a high integration density. You suddenly do not need any additional external components anymore, because everything that you need can be put inside the chips. When you miniaturize the transistor, also there's another effect. The threshold voltage of the transistor becomes smaller. Yeah, and this could be an advantage. This actually means you can actually lower the supply voltage, for example. This will reduce in total your DC power consumption. Your chip become more efficient. And then there's another effect that you also get when you shrink the transistor. Yeah, when the length and the width of the transistor channel becomes smaller, suddenly you can switch the transistor even more faster. The idea is following. You know that the source and the drains are where you actually put the charge carrier. The source is the source of the charge carrier. Of course, when you want to transport the charge carrier, you simply transport it between the source and the drain via the current channels. Yeah, so this is done by applying a gate voltage. When you make the length smaller, then it means you can transport the charge carrier from the source to the drain much faster. Yeah, this means the transistor becomes really fast. So by shrinking the transistor, the main motivation is actually to make the transistor more efficient. But suddenly you also get the other advantage, which means the transistor is faster, and then suddenly you can use this technology also for high frequency application. Okay. When you shrink the transistor, there might be actually some issues that might arise. Yeah, for example, you might ask, is there a limit to how small can you shrink the transistor? Yeah, there is actually one thing that has to be considered. When you make the channel length very, very small, then it means also because the silicon itself is a semiconductor substrate, it is not an isolation layer. So it means when the channel length become really small, we have another problem, which is the leakage, the current leakage. You cannot switch on and off the transistor so easily anymore. Yeah. So even if you switch off the transistor, there will be always some sort of leakage, charge carrier leakage that can transport a small current from the source to the drain, even if you disable the channel between the source and the drain. People want to shrink more because, you can integrate more transistors, right? But when you shrink it too much, then the transistor becomes so inefficient because of the leakage. That's why semiconductor companies come up with several new process techniques, some ideas how this leakage can be somehow eliminated or even, let's say, reduced. People know that from channel length less than 28 or 22 nanometers, the leakage current becomes so dominant. The short part between the source and the drain is hardly a barrier for the free moving charge carriers. In a conventional CMOS technology, you usually cannot really control the thickness of the source and the drain that much. So you have many possibilities for the charge carrier that can be transported between the source and the drain. Okay, let us see what we can do about this. Some companies come up with the idea to limit the thickness of the source and the drain, by implementing what is called the FDSOI technology, fully depleted silicon on insulator. So you simply implemented a kind of oxide layer inside the silicon, and then you implement the n-doped semiconductor for the source and the drain areas. In this way, when you integrate the isolation layer, you can somehow limit the thickness of the source and the drain. So it means the charge carrier that can move from the source to the drain is only in this region. This is a little bit different in the conventional CMOS technology. You have a lot of possibility for the charge carrier to move from the source to the drain. Now it is limited because the channel length is, let's say, has a smaller thickness. Yeah, the idea is actually really quite simple, but the implementation is actually without, because the oxide layer implemented into the silicon is not trivial at all. Yeah, so this is not something that is compatible to a standard processing process. Um, um, you can build an oxide layer on top of a silicon, but inside a silicon is actually not possible. What you can do is that to implement this, that you can use two different wafers. When the FDSOI technology was fabricated or was enabled for the first time, the companies actually simply use two different wafers that are then combined together. At the end, the oxide layer is actually built on top of the silicon on both sides of the semiconductor wafers. But nowadays, this can be done more efficiently. This process has been perfected and patented by the Japanese. This process actually also favored by many companies here in Europe. For example, NXP and ST Microelectronics actually choose to use this for high frequency application. Sooner or later, Infineon might also jump into the FDSOI technology. Okay. So another method to solve the leakage problem is you want to scale down the transistor, but you don't really scale it in a conventional way. You scale it actually in three-dimensional way by using the so-called FinFET technology. Yeah. In the classic planar technique, this is the typical way how transistor is implemented. The source and the drain regions are directly implemented inside the substrate, and the gate electrode is placed then on top of the silicon. Yeah. In the FinFET technology, the source and the drains are etched to the height of a fin. So, or of a fin. So it means the substrate around them, you don't have silicon anymore, or actually the silicon is kept at minimum, so that if there's a leakage, kept at kept at minimum. Yeah. This does not actually solve the actual problem of the leakage current due to the smaller distance, but at least you can reduce the leakage of the charge carrier between the source and the drain. Yeah, and the gates actually surround the source and the drain, so it means you maintain a good control of your current channel that you would like to actually to establish between the source and the drain. In conventional CMOS technology, the technology node usually means the minimum channel length. Yeah. So, but with FinFET technology, the technology node is actually just a marketing term. Yeah. So it actually doesn't say anything about the actual structure size of the transistor. Yeah. So I took this data from IEEE publication, which was actually a publication from TSMC. For example, here the 5 nanometer technology nodes actually doesn't have any transistor structure that has, let's say, a size of 5 nanometer, but instead the physical gate length is 18 nanometer and the fin width is 7 nanometer. So it is actually just a marketing term. Because the transistor is then built in three-dimensional, it becomes smaller in terms of the required chip area. So why this technology is still called 5 nanometer technology node is actually because when the transistor is made in this way, the required chip area becomes so small. So it means this transistor requires less chip area. So the integration density is actually that is actually more mostly important for the semiconductor companies. They just simply calculated what would be actually the required chip area, and then they say this is then actually the same size as if the transistor is made in planar way with a channel length of 5 nanometer. Yeah, in 3 nanometers, the gate length is shrink a little bit to 16 nanometer, and the fin width becomes a little bit smaller, 6 nanometer, but it is not 3 nanometers. Yeah, there's no 3 nanometer structure inside the technology node. Yeah. Nevertheless, it becomes smaller because the transistor is in 3 dimensions. So these are the two methods that have been applied successfully by semiconductor companies to address the leakage problem. Yeah. So the second idea with the FinFET is actually quite clear, right? Because when you don't have any silicon at all, then you simply just have the air. The air is of course quite high ohmic, so it means you don't have any leakage problem. With the FDSOI, you also can limit the leakage problem because the thickness of source and drain is actually quite small. So it means also the leakage can be somehow controlled much better because of the smaller thickness. Okay, but let us think further. What can also be done to address the leakage problem? But at the same time, we would also like to shrink the transistor. The main idea is also we would like to make the transistor faster by making the transistor smaller, or by making the distance between the source and the drain smaller. Because when you want to transport the charge carrier, let's say here, from the source to the drain, the distance plays a major role. Clear? Yeah. So the smaller the transport time, the faster you can transport the charge carrier from the source and the drain. Then the transistor becomes very interesting for high frequency application. We have seen how we can do that. We can just simply shrink the transistor, and then we get exactly what actually we want. What do you think is also possible to make the transistor faster? What can we also do if we want to minimize the transport time to transport the charge carrier from the source to the drain? By not simply making the channel length smaller. Yeah, in physics, we say actually there are 3 most important parameters. Like if we are talking about the time, when you actually move something from one space to another space, then you have the length or the distance between the 2 spaces. And then another parameter that is also important for the transport time is, of course, also the speed, how you actually transport the charge carrier between the source and the drain. So it means actually the velocity of the charge carrier is also important. What can you do about this? If you don't want to make the channel length smaller, but you want to reduce the transport time of the charge carrier between the source and the drain, you can, of course, also make the charge carrier move faster between the source and the drain. How can you do that? Yeah, then you can actually dope the substrate differently. Yeah, you make the charge carrier mobility in the substrate actually as high as possible. Is it clear? So, but my question is actually, why is it not being done successfully actually in a standard CMOS technology? The idea is actually really simple, right? So the main motivation for the high frequency applications that you would like to transport the charge carrier faster from source to drain. Yeah, the easiest way is just to make the channel length smaller. Then when the distance is smaller, then the transport time is also smaller. The transistor is faster. The parasitic capacitance is also smaller. If you make the mobility of the charge carrier in the substrate actually higher, then you can also minimize the transport time. But this is something that you do not really do with a standard CMOS technology, at least not for the field effect transistor. Why is it not done? Yeah, this doesn't. This actually is counterproductive, because when you change the mobility of the charge carriers of the silicon substrate, and the silicon substrate become quite low ohmic. So it means also you will also increase the problem with the leakage, because the part between the source and the drain is quite low ohmic. Even if you do not really switch on the transistor, there will be high leakage current between source and the drain. That's why you do not change the conductivity of the substrate. by increasing the mobility of the charge carrier. But the idea is actually really cool. Yeah, that's why this idea is actually also used, but not with a field effect transistor. Instead, this is done with another type of transistor. You get a very high in the base area, and then you make the base as thin as possible so that you can transport the charge carrier between emitter and the collector much faster. But this is not field effect transistor at all. Then why am I talking about this? Quite not not interesting, because it is actually not really CMOS, right? So we would still like to use the silicon technology. Yeah, the thing is, the bipolar transistor can nowadays also implement it on the same silicon technology. So the processing step is actually quite similar to standard processing. You actually only change the charge carrier mobility of inside the transistor itself. Yeah, so you don't really share, you don't really change the substrate because the substrate is actually shared by all other components. This require, of course, additional processing step, but because the bipolar transistor is very easy to fabricate, it costs actually not really that much more. Yeah. So you can actually use the same technology node, the same, let's say, the same lithography machine. 130 nanometer is suddenly even interesting frequency applications. Yeah, so that is actually the main idea about the so-called silicon germanium BiCMOS technology. You simply integrate so-called HBT transistor. That is the reason why, for example, IMEC stay with the 28, use quite old technology node, like for example 130 nanometer. Yeah, Infineon, for example, still use the 130 nanometer technology to make millimeter wave radar chips. Yeah, and this is something that you cannot really compare anymore with the standard 5 nanometer technology. But yeah, the technology is still very interesting. And this is the company where I actually used to work for a long time. Yeah. Application, what can we do with these millimeter wave sensors? Yeah, for all we know, by
recording
certain
in
materials, for example,
progress.
it can penetrate a wood, it can penetrate, will be reflected by a metal objects, yeah, or by a surface that has quite a large amount of water or blood, for example. Yeah. These properties can be used for the active imaging sensor. Yeah. So you can, for example, look behind the wall, who are behind the walls by using this electromagnetic sensor. Yeah. So this, for example, the military application, the millimeter wave sensor. Yeah. In contrast to optical or ultrasonic sensors, the millimeter wave sensor does not require a line of sight to function. So it's quite similar to, for example, your smartphone. You don't need to be outside to make a phone call. Yeah. You can also stay inside the room to make a phone call. And you still can maintain a connection to the baseband, for example. Yeah. We call the sensor active imaging sensor when we need a stimulus, or we need a kind of excitation that can illuminate or irradiate an object. Yeah. In the case of millimeter wave sensor, the stimulus is the electromagnetic waves. Yeah, there are mainly two operating principles. It's actually quite common one. In the reflections mode, the imaging of the object is usually generated by the reflections of the waves. It's actually quite easy. You can use many different stimulus for that purpose. You can use, for example, a pseudo-random noise sequence for the transmit signal. When you do that, then the signal is actually reflected by check, and you will get again the same sequence in the receive part. In order to get the delay information out of the receive signal, you can, for example, do like cross correlation of the transmit and the receive signals. Yeah, and then from the cross correlation signal processing, you can obtain then the delay informations. Yeah, so it's actually quite simple. Since the electromagnetic waves travel always with a constant speed of 3 times 10 to the power seconds, if you then information about the distance, because the delay itself, the tau, is simply 2 times the distance over the speed of the electromagnetic wave, which is the c. So that is one of the active imaging. Another principles that is also used by millimeter wave sensor is the transmission mode. In the transmission mode of the active imaging sensor, that's power that you